Brandon, I think we can start.
Okay, yeah. So today is day 2 of bootcamp. We're going over drivetrains, manipulators, and machining.
Go to the next slide. Brendan, go to the next slide. Okay.
Is it not showing up?
Yeah. Okay. So there are two different kinds of drivetrains, the tank drive and the holonomic drive. The main difference between them is that the tank drive can only move forwards and backwards without turning, but in order to go sideways, it has to turn. While holonomic drives, on the other hand, have wheels that can rotate in any direction, so these drives can essentially move whichever way they want to move without having to turn. Holonomic drivetrains have many different variations, while tank drives do not come in different variations like holonomic. So each type of drivetrain has advantages and disadvantages to it. Tank drivetrains, which have tank wheels, are simpler to design, build, and program, as well as easier to drive. And they also have potential for high speed and pushing force, but are less agile than holonomic drivetrains, which means that there's less maneuverability. Brandon, next slide.
Okay,
I think it's just taking a little while to load. Holonomic drivetrains, on the other hand, they're more agile, which means that they have increased maneuverability, but they're also very challenging to program and drive, as well as having less potential for a high pushing force, meaning that they can get knocked over much easier.
so wheel scrub is when the sides of a wheel in a tank drive drag across the floor while the robot's turning. So this causes a lot of friction, which slows down the turning. If you see in the drawing below, the robot is turning, and then there's wheel scrub on the 4 outside wheels. So tank drives can either be 4-wheel or 6-wheel and 8-wheel. And so when you use a 4-wheel tank drive, you can use Omni Wheels to reduce scrubbing. And also when you're using the 6 and 8-wheel, the middle wheels can be put lower than the outer wheels. So what this does is it raises the robot a little bit. So when it's turning, it's not turning on all of the outside wheels. It's just turning on, like say you have 6 and the middle wheels are drop centered, then it'll be only turning on 4. And then if you don't want to do a drop center, you can put Omni Wheels on the outside. So as you can see, there are 4 Omni Wheels on the 4 corners of the robot. And so these Omni Wheels allow it to turn with less friction. Is the video showing up for you guys?
We can't see it. Okay.
Are you not able to see it?
Now we can.
Brendan, are you using a Wi-Fi?
Yeah.
Yeah, the signal is coming off very slow, so you want to try a better Wi-Fi spot?
I can't really move. Ananya, can you share?
Yeah, sure. Give me a sec.
That's a lot better, Nani.
So yeah, that's just how a tank drive moves. Ananya, you want to do Magnum Drive?
Yeah. One type of holonomic drivetrain is a Magnum Drive. So the Magnum Drive has 4 Magnum wheels, each with its own motor, and each wheel has angled rollers at 45 degrees, which allow the drivetrain to move in all directions. But also because of these angled rollers, the drivetrain can also be easily pushed over. This diagram shows how the Magnum drivetrain's wheels move when the robot moves in different directions. You should have a closer look at this diagram when we send the slides out tonight, so you can have a better understanding of how the Magnum drivetrain moves. And this is an example of that.
Okay, so the Omni Wheel is the second type of wheel that's used on holonomic drivetrains, and the Omni Wheel are weaker than the tank wheels. They have rollers on their they have rollers on their circumference, allowing them to move forward, backwards, left, and right without having to turn, but they cannot move diagonally like Magnum wheels. Can you go to the next slide, Bren? Oh, Ananya. There are several kinds of holonomic drivetrains that use Omni wheels. One type is the Kiwi. This drivetrain uses 3 wheels positioned in an equilateral triangle, all 120 degrees apart. They are harder to push over and stronger, as well as maneuverable, but they have low traction and can be easily spun and moved. Kiwi drivetrains are more complex to build and harder to program, so no one actually uses these in FRC much, although they do show up in FTC sometimes. The 4-wheel Omni is a type of drivetrain that is similar to the Kiwi drivetrain, but instead of 3, it uses 4 Omni wheels in a traditional tank orientation. An H-drive is a special kind of Omni drivetrain that uses 5 wheels instead of 4, whereas 4 Omni wheels in the traditional tank setup, but there's also an additional one in the center, and this is used to strafe. H-drives have low traction and are very agile and are actually easier to write code for. The next slide. And this is an example of an H-drive.
So the next drivetrain we're going to talk about is the last one, it's a holonomic drivetrain called the Swerve Drive. You might recognize this from our robot from last year. So this is known as the ultimate drivetrain. It has the maneuverability of a H-drive and the pushing power of a tank drive. Each wheel can be operated and turned independently of each other because there are 2 separate motors for each wheel. So the Swerve Drive can move in all directions no matter what orientation it is because the wheels can freely rotate. It's hard to design and build and definitely hard to program. And this is the video of our Swerve Drive. You can see our robot was spinning a lot while still moving the direction it wanted to. That's one of the pros of having a swerve drive.
Alright, so to complete missions during the FRC game, more than just the robot's drivetrain is needed, so teams must build mechanisms and manipulators on the robot to interact with the game elements in order to score points and complete missions during the game. There are several kinds of manipulators that we'll cover today. The first one is an arm. The arms are mechanisms that are used to raise and lower game pieces, and they work similar to how a human arm works. Robot arms have a pivot point where they rotate about just like how a human. Arms are more simple to build and more maneuverable than elevators, but they are also not as compact. Arms can reach over other robots, but it may be harder for them to lift heavier objects and game pieces. This is an arm in motion.
So the next mechanism is called a 4-bar linkage. You might recognize it from a basketball hoop. So 4-bar linkages are often used in arms, and they keep both ends at the same orientation, no matter how high it moves. So if you think of a basketball hoop, it keeps, I forgot what the board is in the back. It keeps the board of the basketball hoop in the same orientation, no matter how high it goes. And then here's a 4-bar linkage shown with the small robot. So as you saw in the video, the red piece stayed in the same orientation, no matter how much it moved.
Elevators are a mechanism and they're used to raise and lower game pieces by working in multiple stages, but they can also be combined with other mechanisms like manipulators. And they manipulate the elements in the game. Like arms, elevators can be used to complete missions during the game by moving objects vertically, but elevators are more compact and more complex than arms. In a cascade elevator, all sections of the elevator rise together, while in a continuous elevator, each section rises separately, starting with the first stage.
The slide isn't changing for me.
Oh, it's not? Okay. Can you see it now?
Yep. Okay, so here we have two different videos. We have one of a cascading and then one of a continuous elevator. For me, the videos aren't playing.
Okay, I'll just go on. I played them a couple of times, so. The scissor lift is a very uncommon type of elevator that we don't like or actually ever use because it is extremely heavy and it becomes increasingly more unstable as it grows taller.
So the next is a shooter. We use it to shoot game pieces into goals that are probably higher than the robot. It's good for small round game pieces or games where you have to move lots of game pieces really fast. And then you can see on the right, there's a wheel shape that's called a flywheel, and we use it to keep it spinning. We use it to maintain a constant RPM. So shooters, it really depends on the game, but yeah, like our last game we used a shooter because we had to move a lot of those small yellow balls very fast into different targets. And so there are two different kinds of shooters, two main different kinds of shooters. There's one with a hood on the left, as you can see. So the hood determines the trajectory of the projectile. And there's just one wheel on the bottom that shoots it, that propels it out. And then there's the double wheel. You might have seen this in like a football launcher. This double wheel shooter, the angle of the shooter determines the trajectory. And so the next is a turret. So a turret is basically a rotating shooter. As you can see in the picture, there is the wheel on the bottom, which powers the balls, and then a hood on top, which can aim. So this turret can rotate on a horizontal axis, and it can shoot multiple different directions pretty easily. It's good for hitting like multiple different targets when you're parked in one spot, but it's harder to design than a normal turret, than a normal shooter. So here's an example of our hooded shooter. If you can see on the top that hood, we actually have two pneumatic pistons that can change the trajectory of the ball. And then it's not on here yet because this is an older video, but we added flywheels.
So an intake takes in and it holds the game pieces. Most intakes use wheels or grippers or even a mix of the two and are attached to the end of an arm or elevator. Last year, our intake, if you look at the bottom, it used wheels that pulled balls into the robot and held them in a storage type chamber. This was our year. I mean intakes.
Okay, so the next is a gripper. Grippers are used to clamp down objects. It's pretty simple and it's not hard to build. I think we used one in our deep space robot. So the way it works is it's powered by pneumatics, and then you can use the pneumatics to open and close the claws, like the one you can see here. It has two claws, and then there's probably a piston further back. So when it pushes out, it opens, and then, yeah, when it closes the claws. And then here's a video of a gripper in action.
Alright, machines. So a drill press acts as a drill, but it's more precise. You work it by turning it on and having it turn really fast, and then lowering the drill bit into the piece you're trying to drill. When you're using a drill press, there are a couple of things you should keep in mind. You need to make sure you center punch the hole before you drill. We talked about center punching yesterday, but just as a reminder, you basically use it to indent into a piece of metal to prevent your drill from moving around. And you also want to make sure that your piece is secure so that no one gets hurt while using the drill press. We talked about hacksaws and reciprocating saws yesterday, and bandsaws had the same function. But with a bandsaw, the blade continuously rotates to cut the material, usually wood, plastic, or metal. So you're not the one that's holding the saw. When using the bandsaw, it's important to make sure that the piece you're cutting is flat on the table and that you're using the right blade to cut it. So when you cut with a curve, you want to make sure that you make relief cuts, which is basically just removing the saw and placing it again to reduce the stress on the blade, because you're trying to cut a curve with a straight blade, which puts more pressure on the blade.
Okay, so next is a sander. It does like similar thing to the file which we talked about yesterday. It's basically rotating sandpaper, so it does it for you. All you do is keep the piece flat on depending on which way the sander's rotating, we can show you in person. But you should keep the piece flat on the table and then slowly push it in. So this sander right here, it has two options. There's one which has a belt and one which has a disc. With the belt, you would probably be pushing it against that gray bar and then just slowly moving the piece down. And then on the disc one, you would be setting on the gray table and then moving the piece slowly into the disc. So the next machine is a lathe. This is used for cutting round things. So the lathe rotates the stock horizontally, and it actually keeps the bit in the same place while you can move it. And so we usually use this with like hex shaft and stuff like that. And then so this creates rotational symmetry, so it should be the same any way you rotate it. And then there's also, I'm not sure if you can see it, a small screen there, which is really accurate, and it tells you how far you're going. Okay, so next is the mill. The mill has a different kind of bit in it. And so the mill, what it does is it cuts, but you can change the axis that you're cutting on. So there's a table which moves up, down, left, right, in front and back, and then you just lower the bit into that. So next we're going to do a Kahoot on this. Yeah, so for the person who chose tank and mechanism, the two kinds are tank and holonomic. A mechanism and swerve are different kinds of holonomic drivetrains.
So whoever picked the Omni is a type of holonomic drivetrain, and like Brandon said in the first question, the two main types of drivetrains are tank and holonomic, while Omni is a specific type of holonomic drivetrain.
Yeah, so tank drives are actually really good at pushing against other robots, but the problem is like turning scrub and other factors make it less maneuverable than a holonomic drive. Yeah, so holonomic drivetrains are actually harder to program than a tank drive, but they're more maneuverable, which is a benefit to them. Yeah, so holonomic is a classification of a drivetrain, and swerve is the actual, what we call ultimate drivetrain, because while it's really hard to build, design, and program, it is really good at maneuvering and also pretty good at pushing. Tank, for the person who chose that, isn't as good as maneuverability as swerve, but it's also really good at pushing.
Like we just said, the swerve has really good pushing power and it's very maneuverable, but the main disadvantage of the swerve drivetrain is that it's difficult to design, build, and program. But if you can build and program it and design it, it's called the ultimate drivetrain because it has so many advantages to it.
It is harder to drive than a tank drive, though, so you guys were also correct. Yeah, so it does use Omni Wheels, but the wheels were in the shape of a H, which is why it's called a H drive. Yeah, so these are called Magnum wheels, and they're used by the Magnum Drivetrain. Omni Wheels are a different thing.
Arm shooters and elevators are all type of manipulators, and if an outtake, if you might be thinking of an intake if you thought that was a manipulator, but yes, arms are types of manipulators.
Yeah, so when you're building arms, they need to be able to reach out and stuff, which makes it a lot bigger and bulkier. So that is one reason why you might choose an elevator over an arm.
This is a cascade elevator, and in a cascade elevator, all sections of the elevator rise together.
Okay, so I think we're done.
Yeah, I mean, unless anyone has any questions about today.
I guess we'll see all of you tomorrow.
All right, see you tomorrow.
Bye, Jake.
Bye.